So welcome all to week 10 tutorial for the course Deep Learning. So I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So today, what I'm gonna cover broadly is CNNs, and I'll try to motivate it using the image-based task. Okay. So it would be more related to CNNs only. And during today's session, I have taken many images from slides prepared by Professor Balamurgan and Professor Preeti Jyoti from their respective courses at IIT Bombay. So, what is CNN? CNN is a algorithm, is an architecture that has been proposed to process image data. Okay. So, if you look at an image on your phone or image that you are seeing right now, it doesn't look like numbers that you are passing to your normal deep neural network, but the way your computer stores an image is always in form of a number. For example, this is a representation of a grayscale image. By grayscale, I mean it has only like shades of black and white. So 0 means black and 256 means white. So this image is generated by like numbers between 0 to 256 denoting the gray, like how dark it is or how bright it is. Okay. So you can break your images into pixels, and every pixel further can be represented by a number. So an image is nothing but a some m cross n matrix. Okay. And this you did when you were like doing MNIST data set also. So you had a 10 cross 10 image. You converted that image into a single vector and then passed it to a neural network. Okay. The accuracy was definitely not that great if you just use some vanilla neural network. So we'll today see architecture called CNN that can help you improve your accuracy. And there are other motivations also for using this kind of network. Okay. So for example, if you look at this particular image only, if you would have used, let's say, some vanilla neural network, one option that you could have taken is that for the first, how you could have created a vector for the input layer. So first you would have taken the first row, and on top of it you would have stacked the second row, then your third row, and so on, right? So the so the entry over here and here are not related to each other. So the entries that you're passing are not in a continuous manner. Whereas if you take a 2D image, because this entry and this entry can be related. So if you are doing some operation on your 2D image, that can be more useful to you. Okay. So this is one thing that I wanted to mention, that your images are nothing but m cross n matrices. Okay. At least for the grayscale image. Okay. I'll cover some details from perspective of your image processing also, so that the tasks that you are doing are more clear to you. Okay. So the first thing that I talked was related to grayscale images, but in reality we have more of color images. Okay. So there are many ways to represent a color image. Okay. So one of the most common way is to represent it using RGB. So what does this mean is that any color that you see can be created using some like ratio of red, green, and blue. These are your primary colors, and you can create any color using the using appropriate ratio of these colors. Okay. Again, how many colors you can create depends on the like the values of range of R, G, and B. And let's say if you vary your R between 0 to 256 and G from 0 to 256, then you can create 256 into 256 into 256 unique colors. Okay. So like these days you might see like brands advertising TVs or mobiles, that you can see more colors on those kind of screens. That generally means that they allow a broader spectrum of red, green, and blue. Hence, they are able to generate more number of unique colors. Okay. So, like if you want to represent a color image, it is just a superposition of R, G, and B, and all these R, G, and B are again some m cross n matrices. Uh, this will also be m cross n. So any color image can be represented as a tensor of size m cross n cross 3. Okay, this 3 is its depth. Okay, there are other variants also to represent. I think I'm not very sure, but there are variants where people use cyan, black, magenta, and there is I think one more color. Using those combinations also you can generate those colors. So this is one of the most common and used variant to represent your images. And there are other variants also, like if you at some time in your life, if you do some image processing course, there you might encounter this kind of things. Okay. So what are the some common tasks that we might be interested in that are related to images and we might be interested in doing? Okay. So one task can be something that is known as contrast adjustment. Okay. So what do we mean by contrast adjustment? If you look at this particular image, it is slightly towards a blacker tone. Okay. So the difference, if you see, the lowest contrast that we can see is around 100, and the highest that we can see is around. So these are the pixel values. So most of the values lies between, let's say here it is 70 to 160. Okay. So because there is a not a very large spread in terms of pixel value, so we are not seeing clear bifurcations in the images. So we can adjust it by making this bifurcations more pronounced. Now, if you look, blacks have gotten more black and whites have gotten more white. So there is a spread in the values that pixels are taking. So this image looks better. So this task is known as contrast adjustment. Okay. So second task that that is important is something that is known as noise removal. Okay. So let's say somebody has added some noise to your data. Then how do you remove that kind of noise? This is again an important task. So this was your original image. Somebody has added noise to this image. Then there are two different algorithms that they have tried to use to remove the noise. This one has not been able to remove the noise completely. This has done slightly better, but still it is not very close to the original image. Okay. Okay. Another important task that you might be interested in is your edge detection. Okay. So where your edge is like where your value of color change like, so if you look at this point, so from here on you have blacks over here and here you have white. So these can be an edge. And similarly, like for any image, you know what an edge is. So edge detection is another common task in image processing. Uh, Next task that I'm going to discuss over here is image restoration. Okay. So you might have some old photos in your album where your photos has been like that's not in a very good condition. You want to fill in these positions and restore your image. This task is known as image restoration, or it is also known as image imprinting. Image imprinting is slightly more than image restoration. So in image imprinting, you can also do things like let's say if this portion of the image was not available and you want to fill in this portion of the image, then that would also fall under the task of image imprinting. There has been many new AI apps and websites where you can sort of change the resolution of your image by filling in some new objects. For example, if your phone clicks pictures in rectangle, okay, and you want to post it on, let's say, Instagram in as a square image, okay. So one option that you had that you used to do earlier was to either crop your image in form of a square image, okay. Another option that you could have used is fill in this uh, space by white or some blurred kind of image to make it square and then post it. We used to use these kind of things. Now what AI apps are suggesting that rather than filling this space by some blurred image or by white spaces, we can fill in it with something that is related to the existing image. For example, if it is a scenery where you have mountains and those kind of things, probably they can fill in this space by clouds, and they can fill in the bottom space by some greenery, right? So those kind of things are being done, and that would fall under the task of image painting or image completion. Another very important task is image segmentation. This has a lot of applications today. So image segmentation is segmenting your image that are of importance to you. For example, you wanted to like identify any animals in this image, then you have to segment out that particular image. This falls under image segmentation. So there is a lot of research and ongoing work in the area of medical image segmentation. So people want to, for example, from your X-ray, you want to segment out the exact location where you can see the fracture or those kind of things. Or from a MRI of your brain, if you are doing some task like cancer detection or those kind of things, so you want to segment out the cancer cells that are present in that MRI if it is present at all. Okay. So this is another thing. So these are some very common image related tasks that people might be interested in doing. So if you are like learning CNN and you want to apply it on some tasks, so these are the kind of tasks that you might apply it on. Okay. Okay. So CNN is an abbreviation for convolutional neural network. Okay. So for the past sort of 9 weeks, we have been doing neural networks. So we actually know what is neural network. The only term that is new to us is something that is convolutional. Okay. So before I go into what is convolution, do you guys have any doubt in the content that I have discussed so far, like these tasks that I have discussed? If you have, you can please ask. Like how an image is represented as a matrix, like anything related to this task that I discussed. Okay. So convolution is a mathematical operator, okay, so that acts between two functions. Like this is the definition that I have copied pasted from the Wikipedia straight away. Okay, so convolution is an operator. It is generally represented by this star kind of symbol, okay, and it acts between two functions and is given by integration from minus infinity to infinity f of t. So the output of this operator will again be a function. So f convolution g at that point t is given by f of t minus tau into g of tau d tau. Okay. So if you look at the discrete version of this, like whenever you go from continuous case to discrete case, you replace your integration by summation, right? So if you look at the discrete case of this can be given by summation from minus infinity to infinity t minus tau g of tau d tau. Okay. So what actually this thing is doing, you can see it in this way. Let's say you have some function values recorded at different time level. Okay, so for example, let's say you have recorded f at time t is equal to 5, t is equal to 4, t is equal to 3, and so on. Okay, and you like from somewhere that you are interested in finding out some value which not only depends on your value of function f at t is equal to 5, but also on values preceding it. Okay, so what you want to do is you want to take the weighted average of your values uh, for your like of function f around that particular point. If you see, this summation varies from minus infinity to infinity, right? So it will also include values t is equal to 5, t is equal to 6, and so on. So it will be sort of a weighted average kind of a thing. Okay, so this is from minus infinity to infinity, but you can also restrict this thing from, let's say, minus a to a. Okay, now why is this kind of thing important? I'll try to motivate it from this figure. Let's say this is my image where I want to find out the portion where I have my house. Okay, let's say I look at this point only. Okay, by looking at this green point, I cannot tell whether this is my house or not. Okay, but if I look at its neighborhood structure, let's say, okay, let me change the color. Let's say if I look at not just this point, but also some neighboring pixels, then I might infer something more about it. Okay, so these kind of applications are possible where you just need not focus on the value of function at that particular point, but you take some weighted sum of the functions at values preceding it and after that. Okay, so for example, so this would look something like if we have, let's say, some weight. Okay, if I have some g of tau as, let's say, 1 over here, 0.1 over here, 0.01 over here, 0.1 here, 0.01 here, then it would look something like uh, f of 5 plus 0.1 into f of 6. This is t is equal to 6, this is t is equal to 7, right? Plus 0.1 into t of 4 plus 0.01 into t of 7, and so on. So this is how, if you look at discrete version of your convolution operator and you bound your convolution operator rather than going from minus infinity to infinity, if you go just from minus a to a, this is how your usual convolution operator would look like. Okay, so we want to replicate something similar for a 2D image. Okay, that's why this particular algorithm is known as convolutional neural networks. Okay, so how do you, so this whatever formula that I had written is just for one dimensional case. Okay, so how do you extend it to a two-dimensional case? So let's look, we'll sort of look at how we can extend it to a two-dimensional case. Okay, so let's say this is some image that you have. Okay, and you want to, let's say, convolve it with some 3 cross 3 matrix. Okay, so there are 3 possible options by which you can do this kind of convolution. Okay, let's say you want to start from this particular thing. Okay, so first option is that you map this red dot to red dot over here. Okay, so then how would this operation look? Let's say this is 1 2 3 4 5 6 7 8. Then this one would be mapped here 2 3 4 5 6 7 8. So whatever would be the value of your image over here, let's say this is my W matrix, this is my I matrix. So it would be I11 into W11 plus I12 into W12 and so on. Okay, so this would be the value of a convoluted thing that you would obtain. Okay, another option that you have, okay, is to map this red dot to this particular point. Okay, then imagine that you have some values available over here also. Okay, and one more layer, then this point would be mapped to this point, this green point over here would be mapped to this green point, this orange point would be mapped to this orange point, and so on. Then you can multiply it with each other, and then you can add it up to get your convolution. Okay, this would be more clear when we do some examples based on it later on. Right now I'm just trying to tell you the ways in which you can convolve in 2 dimensions. Okay, another option is, like, let's say if you want to find your convolution at this point. Okay, then what you do is you map this point to the middle of your filter. Okay, so there are 3 options. You can map it to middle of your filter, you can map it to top of your filter, you can map it at bottom of your filter. So mostly CNN would use the option where you map your point to the middle of your filter and then obtain the value. Okay, so this thing by which your image are convolved, this thing is known as filter. Okay, so let's discuss about some common filters that traditional image processing community used to use. I'm not covering many, but I'm just covering 1 or 2 so that you have an idea how a filter works. Okay, so this is something that is known as mean filter. So how would your filter look like? So your W would look like, let's say this is a 3x3 filter. Then what you want to do is, after you at this particular point, this blue point, if you apply this filter, right, you should get an average value of values around it. Okay, so how you can design this particular thing? You can design it by taking all the values 1/9, right? Okay. So this is something that is known as mean filter. Okay, so you just what will you do is you will place this thing over here and then multiply the individual values and then add them up. Okay, we'll have an example for this. Okay, another common filter that you have is something that is known as median filter. Okay, that filter you can't write in form of your W matrix, but what you do is you place your W over here, and then you look at the median values occurring in this particular like range, and you output whatever is the median. Okay, that is also a filter, valid filter. There is something that is known as okay, I have median filter over here. So if you want to apply your median filter at this point, so that you can see that value 3, if you arrange it in increasing order, so 4 is the median value, so the output would be 4 over here. Okay, similarly you can apply this at other points also. Okay, okay, so this is an example where your mean or median filters can be useful. The example is denoising your data. Okay, so this was your original image, and this is the image after adding some white noise. Okay, because you have added white noise, let's say a noise was added over here, so that particular point has been made noisy. But if you look at its small neighborhood, there is a high possibility that other points actually represent the uh, actual value that there should be in the image. Okay, so what you can do is you can replace this value by the average value in that particular range. Okay, so this is the image that has been obtained after applying mean filter. Okay, so there is also a drawback of using mean filter. What it is, so if you look at the this boundary points or these sort of edges where your value changes, so because at these points also you are taking average values, right? So what happens is this boundaries becomes slightly smoother. Okay, so your boundaries become smooth as compared to your original image. So this is a drawback, but mean filter can be used to reduce a noise to lot extreme. Okay, I'll get back to padding. Okay, let's discuss about padding. Okay, so let's say this is your original image, and you want to apply mean filter to your data. Okay, so you can apply it here by just taking a 3x3 box around it, and then doing the convolution operator as we discussed. Okay, you can also, if you place your blue point over here, still you can get a 3x3, and you can apply the you can obtain the result. But what about this particular point? Like if you take this as your middle point, then placing a 3x3 box will go outside the image, and you don't know these values. Okay, so these values are not available with you. Then how do you apply your filter at these points? Okay, so one way is like when you apply filter, you can sort of ignore these points. Okay, and the new image that you will obtain by applying filter at all the points would be of reduced size. Okay, so the new size would be just this much, whatever I have marked in black. Another option is you can fill in these values by some dummy values. Okay, one such way to do, and that thing is called padding. So when you fill in these values that are not existing in the image with some dummy value, okay, that thing is called as padding. Okay, so one option of padding is zero padding. So what you do is for these values you replace it by 0. Okay, so this is zero padding of length 2. Okay, so you have added 2 extra rows and 2 extra columns with value 0. Okay, so there are other kind of paddings also. Okay, I don't recall their exact names, but what we do in that thing is, so if you, let's say you want to add a pad over here, what you will do is you will copy the values that are available over here. So it would be 1 2 8 2 4 1 2. Okay, why is this logical is that whenever you sort of click your picture, generally the important information that you have is in the middle of your picture. Okay, so if you are clicking somebody's picture, the person would be in middle, and generally the boundary is sort of the background or the scenic things. Okay, let's say this the top row represents your sky. Okay, then padding it with sky makes more sense by rather than padding it with some just some black noise or 0. Okay, so this I think is known as duplicate padding or something like that. And if you want to add one more layer, then the second row would come into picture. So it would be 1 3. I'm not sure whether it is called mirror padding or duplicate padding. Like based on your usage, you can check. Okay, this is one option. Another option is that you can just fill in any random values, that would be random padding. There is other option also that is known as mirror padding. So what you do in that is you sort of roll this image up. So now if you want to add a pad over here, extra over here, you won't copy values from here, but rather you will copy from the last row. Okay, so you are sort of joining this thing. Okay, and here you will copy from here. So there are different kind of paddings that exist in literature. Okay, so if mainly zero padding is used for CNNs, but if you are doing some different kind of task where you might where your zero padding is not helping you, so just to let you know that there are other kind of padding that also do exist. You can check out those in literature. Okay, so we discussed about median filter. Another very common famous filter is Gaussian filter. So you can see that towards the middle values are high. So how does your Gaussian distribution or normal distribution look? It looks something like this in one dimension, right? So you have high values towards the mean and lower values when you sort of go away from the mean. In the 2 dimension also, it would look something similar, like you have a tomb in sort of high values in between, and slightly moving away, it will have lesser and lesser values. So this is something that is on Gaussian filter. Okay. So this is used to for smoothing effect. There is another interesting filter that I recall right now, that is known as speed blur filter, that I haven't included, but I'll could have. Okay, so this is an interesting kind of a filter. If your time permits you, if you want to try, you just search speed blur filter. So when you try to click image of something that is in motion, generally what happens is you won't get a very clear image, but slightly hazy kind of image. So speed blur filter, what it does is it converts your normal image into speed blur kind of images. Okay, so this might motivate you to find filter that would reverse this thing. So let's say if you are clicking some image and you are getting slightly blurry image, what is the filter that you should apply so that you get a better crisp and clean image? Okay. Okay, so there is one question that I've included over here. I think this is relevant for your assignment. So there is this filter that I have written. Okay, if you have, let's say, some grayscale image. Okay, what do you think this filter will do? I'll wait for your answers. Like, what do you think this filter will do?
Sharpen.
Okay, we'll see. Why would it sharpen?
Age detection.
Yeah. Okay, so we'll see what would happen. Okay, so how does a filter work? So let's say this is your big image. Okay, and we are applying your filter, let's say, at this point. Okay, so what will come here over here is your value 8. Okay, and in the neighbor you will have -1, -1, -1, -1, -1, -1, -1. Okay, now when will this value so whatever you obtain after convolution, when will this be 0 and when will this be non-zero? Okay, so it will be close to 0. Okay, let's say if my this value is x, 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 and this is also x, that means all the values are same. Okay, or at least they are very close to each other. Then what will happen is, if I multiply and add them up, so this would be minus x minus x minus x, this would be minus 8 times x plus 8 times x, it would be 0. Okay, so if the values are very close to each other at all these points, okay, then the values that I'll get is 0. Okay, now let's say my values are not same. Okay, so let's say uh, something like this. So values over here are y, 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 y. Okay, so what would happen is the value that I would get would be non-zero, right? So non-zero would mean black, right? And non-zero would mean some shade of some brighter shade of white. Okay, so that on one side you have some other values, let's say x, 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 and at other points you have y, 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 y. So what does this mean? This means that the color is changing over here. Like around this point, this particular point, this green 8 point, what is happening is the color is changing over here. So that would mean that this point is on boundary or edge. Okay. So what does this filter do is it will give you value 0 for points that are not on edge. Okay. And it will give you value non-zero, right, for values that are on edge. Okay. So this filter is sort of used for edge detection. Okay. Yeah. For example, if you look at this particular point, this point, okay, and look at a small neighborhood. So all the values are same. So the filter will give 0 value. That's why we have black over here. Okay. But if you look at, let me choose a color. If you look at this particular point and you take a neighborhood, then there is difference in value. So the value that you will obtain is slightly brighter color. That's why you see an edge over here. Okay. So this filter is an edge detection filter. Okay. Any doubt in content, whatever we have covered so far? Right now, it has been more of a recap of image processing thing. Right now, we will delve into a deep learning domain. So before that, any doubt in the question that we discussed or anything else? Okay.
No, sir.
Okay. Okay. So till now, I gave you a brief idea of what convolution would look like, right? But let's try doing this convolution operator at some points. Okay. So we have not added, this is my image. This is just a binary image. Binary image is that 1 means white and 0 means black. This is as simple as that. Okay. So we haven't added any sort of padding right now. Okay. So we can't do convolution operation over here, because if we want to match this middle one to this point, it is not possible, as it would go outside the right image. So let's try from the point where it can be mapped. So this one would be mapped to this one. We can try highlighting it if it is visible. Yeah, this one would be mapped to this one. Okay. Then how would my convolution look like? So this point gets multiplied by this point because this gets overlapped. So this would be 1 into 1 plus 1 into 0 plus 1 into 1 plus 0 into 0, again plus 1 into 1 plus 0 into 1. This is 0 into 1 plus 0 into 0 plus 1 into 1. So there is 1, 2, 3, 4. So the value that we would obtain is 4, right? Yeah. So this is how first entry of my convolved feature would look like. Okay. So the first entry would be 4. Then what we will do is we will slide our window or slide our filter, and from here we will move to this point. Okay. And then again do the same operation on this particular thing. We'll do the same operation, obtain the value and write it over here. Again we will slide our window, and sliding the same way we will obtain a convolved feature. Okay, this is the core idea behind CNN. Okay, so there is one formula that is pretty useful and will help you. So you know what is padding now, you know what is kernel width. There is something that is missing, is known as stride. I'll tell you what stride is before we go into that formula. Okay, when I told you that how do we obtain this convolution feature, what I did was, let's say I started at this point. The next point that I'm going to go to is this next point. Okay. So I'm not skipping any point. I'm just going to the next point. Then my stride is 1. Okay. So what if my stride is 2? What does that mean? Stride 2 means, let's say if I started from this point, I won't go to this particular point. I'll straight away skip to this point. Okay. So there is a gap of 1 if I have my stride is equal to 2. And similarly, by stride 3, 4, you can say that you would be skipping some of the points in the process of your finding your convolved feature. Okay. So right now, let's assume that if your image is a square image, so the size is a square image, and that is a m cross m image, or let's write it in the notion that they have written. This is n input cross n input image. Okay. And your pad size is the padding that you have done. Okay. N out represents the size of your convolved feature that you will obtain. Okay. Kernel width is the width of your window. So this was your convolution filter or the kernel. This is also known as kernel. Okay. So its width is 3. Again, we are assuming that this would be square. Okay. So the number of so this is a, so if you do this kind of convolution, the convolved feature that you will obtain would also be a square matrix of size n out cross n out, and that n out is given by number of in plus 2 times the pad size minus your kernel width divided by stride, and you take a floor function of this. This bracket is not the normal bracket. You can see this is the flooring of your values that you obtain, because your stride can take sort of any value bigger than 1, right? So this value that when you obtain by dividing by this stride need not be integer always. Okay. So need not be integer. Then this flooring thing comes into picture. Now because you are flooring this particular thing, that's why you add a +1 towards the end. Okay. So again, like if for somebody who don't know what a floor function is, so floor function, what it does is, so if you have some, so floor, it's a function. It's a function from R to Z. So R is your real number. This is your integer. So it will convert any real number to its near, I won't say nearest, but the just below integer. I'll just tell you what this floor function is. Let's say you already are inputting some integer to it. Okay. So it will give you output that particular number only. So if you input any integer to your floor function, it gives you that particular number only. Okay. But if you input some decimal to this floor function, okay, it will return you the integer that is just smallest to smaller than that particular real number. So what is the integer that is just smaller than 2.14? The number is 2. Okay. So for example, what is the floor function of 4.8? Floor function of 4.8 is 4. It is the number just below 4.8, integer just below 4.8. Okay. Similarly, what is floor of minus 3.2? It is the number just below minus 3.2, that is minus 4. Okay. So we are not removing just the decimal, but we are looking for the integer that's just below the decimal that you have written. Okay. Okay. So when you apply your convolution, this is the size of the convolution feature that you will get. Okay. So let's look at some of the examples. Okay. So it is a 4 cross 4 image. Okay. And you haven't done any padding. The stride is also only 1. and this dark blue thing that you can see is the filter. So the filter is 3 cross 3. Okay, so you can see you can't apply your filter at these points that I am crossing out, because you can't fit a 3 cross 3 keeping these points in center. Okay, so the only points that are left where you would be able to apply your convolution are the middle ones. Okay, okay, are these middle points that
You,
yeah. Okay, so are these middle points, that's why you will get a 2 cross 2 convolution feature. Now you can verify this using also the formula that has been written above. So what does that say? N out, I think this color should be that great visible. So N out is given by N in. So N in is 4 minus 2 times the pad size, sorry, plus 2 times the pad size is 0, minus kernel width, that is 3, divided by stride, floor function, plus 1. So what it is? So this is 1 by 1 floor plus 1. So this is just 1 plus 1 is equal to 2. So we got the size of our convolution operator, which is 2 cross 2. Okay. Now we have included some padding also. So this is a padding of size 1, right? And the filter remains to be of same size, 3 cross 3. Okay. And your image now is 5 cross 5. The earlier image was 4 cross 4. Now this new image is 5 cross 5. Okay, let's see at what points we can calculate the values. So at these points that I'm crossing out, we can't fit a 3 cross 3 filter, right? But at rest of the points you can fit, right? So its size would remain 5 cross 5. Just see and verify that you can, at other points, you can fit in this filter. Okay. So again, using the formula, what is N out? N out is N in plus 2 times pad minus kernel, size of kernel, divided by stride. Stride is again 1 over here, floor plus 1. Okay. So what is N input? This is 5. Now padding is of size 1. So plus 2 minus 3 divided by 1, floor plus 1. So this is 4 plus 1 is equal to 5, and size of my output that we obtained that way also is 5 plus 5. Right. So this is how you can calculate the size of your convolution feature, right? And okay, let's look at some more example. Now again, your stride is 1, but your padding is 2. Okay. So even in the lecture, most of the example that professor has covered, there you can see that the size after convolution has always reduced. Even before your max pooling, the size after convolution has reduced. But if in some application you require that your convolution size needs to increase, then you can include these extra paddings to increase size of your convolution feature. So one motivation to do something like that can be, for example, let's say you want to train an auto encoder kind of a thing. Okay, so auto encoder kind of a thing along with some CNN. So you want to embed the auto encoder architecture using CNN. Then you might might need to increase the size of your features. Okay, there you can use these kind of things. Now the padding is given to be 2. The original image was just 5 cross 5, but the feature that you have obtained is 7 cross 7. Okay, so again, using the formula, you can obtain N out to be 5 plus 2 times padding minus the kernel size divided by the stride floor function plus 1. So this is 5 plus 4, 9, minus 3 is 6. 6 plus 1 is 7. Okay. Okay, so here is another example. So here you don't have any padding, but your stride is 2. Okay, so this is again 5 cross 5, filter is 3 cross 3. So what you did is you started with the, so you can't fit in over here, that you know, because there is no padding, right? So you started from here. Now because your stride is 2, you will skip one thing and go here, right? Again, in this direction also, you will skip one point and you'll come here. You'll skip one point from here and you'll come here. So this is a 2 cross 2 thing that you will obtain. Okay. So these points were sort of blocked because of your stride. Okay. Okay. Now let's try to evaluate using the formula. So n out is nothing but n in is your 5, padding is 0, kernel size is 3. Now stride is 2. Again you take floor plus 1. So this is 5 minus 3 is 2 by 2, floor plus 1. This is 1 plus 1, 2. This is what we obtain, right? Okay, this is including everything. You have stride also, you have padding also. So let's straight away find the formula. This is 5 cross 5 image again. Okay. So n out is 5 plus 2 times padding minus 3 divided by 2 floor plus 1. So this is 7 minus 3, 4. So this is 2 plus 1, that is 3. So you have obtained 3 cross 3 convolution feature. Okay. Any doubt till this point? Now we will see how do we use this convolution thing in our neural network architecture. How do we treat images through this thing? If all these things are clear, then it's just mixing these things up and using them smartly. Any doubt till this point? If you have any doubt, you can ask. Okay, so it's 6:57. We can take a 2-3 minutes break because this is a long 2 hour lecture. You might also get bored in between. So let's take a 3 minutes break. We'll start again at 7 o'clock.
हाँ तो हाँ तो मेरे साथ एक और दीदी थी, तो उसका दोस्त।
Okay. So how does a usual CNN look like is that you will have some input image. Okay. Then you will have a layer of a convolution. Okay. Then would be something called pooling, that we'll see what it is. Okay. And again we'll have convolution, then again pooling, and so on. Okay. So now what we would be discussing is how does a one layer of convolution looks like. So we would be just discussing this part, like how does one layer of convolution look like. Okay. So we talked about two-dimensional filters, right? Whatever we discussed were related to two-dimensional filters. Okay. Now when we look at colored images, okay. So colored images are not your two-dimensional images, but they are three-dimensional tensors, right? So we will require a three-dimensional filter too. Okay. So for example, if this was your image, it had R, G, and B, right? This is RGB. Then if I want to apply, let's say, a 5 cross 5 filter, then I'll have a separate 5 cross 5 for here, 5 cross 5 for here, 5 cross 5 for here. And if we write it together, this would be a tensor of size 5 cross 5 cross 3. Okay. So what used to happen in a two-dimensional convolution, you used to multiply individual elements from here to individual element in your kernel and then add them up. Okay. Similar thing you will do over here, similar thing you will do over here. So you have obtained three values, one from, let's say, R, one from G, one from B. Now what you again will do is you will add all these three values also together to obtain just one value. So if you apply even a 3D filter on these kind of images, you will obtain only one value. Okay. So like if you are applying a 3D filter at this particular point, so you will get only one value. Okay. Then you will again move ahead and so on. Right. So you can just see it like a 2D image only, where this front facing portion is similar to your front facing portion over here, and the rest of the things just fit in that position well, and you will move in this direction only. You will move from here to here, here to here, and this depth, you won't move in the depth. You would only move in this direction, this direction, this direction, this direction, this direction. Okay. Okay. So this is a 32 cross 32 cross. Now depth is 3. Just ignore the depth of timing. And you have a 5 cross 5 filter. Then what is the output convolution feature size? So we just did, so there is no stride over here, the stride is only 1. So this is 32 is your input minus 5, that is 27 plus 1 would be 28. So we should obtain a 28 cross 28 feature, right? Let's go down, and this is what we have obtained. Okay, because we had only one value, its depth is only 1. So after we convolve on some image, you obtain a 28 cross 28 feature. Okay. Now think of this from perspective of a neural network. Okay. So when we did some traditional filters, for example, mean filter or median filter, we had a matrix, right? We had a matrix with entries 1 by 9 everywhere. Right. But what changes in your neural network based filters is that you don't know the values of your this entries of your matrix W. Okay. This is just some W1, W2, W3, W4, W5, W6, W7, W8, W9. You initialize them with some value, and the way you used to do in your normal neural network, you used to train your network using some loss function and backpropagation. The same thing you will do over here. You will tune in your W's, you will change your W's based on the gradient values that you obtain, and you will finally obtain some filter that will do your job. Okay, so you initialize this randomly, you will progress, and then at the end you will obtain some values. You will update it using some optimization technique, gradient descent probably, and then you will obtain the final filter. Okay. So for CNNs, you don't know the values of your filter. Okay. You just initialize with them with something, and then you learn those weights. That is the difference between classical image processing and what we are doing in CNN. Okay. So now let's say this is a 32 cross 32 image across 3. Okay, so if you want to use this in a flattened version in a neural network, so what would be the size of input layer? It would be 32 cross 32 cross 3, right? And if you have only one filter, how many weights you have to learn over here? If it is a 5 cross 5 cross 3 filter, so it would be 5 cross 5 cross 3 filter. Okay. Now, if you are just at your initial layer and you have only 5 cross 5 cross 3 weights to be learned, so these are very less number of parameters that you are learning. Like if you look at the complexity of tasks that you have at hand when you treat images, for example, if you want to detect edges, or if you want to complete the image, if you want to do image restoration or image segmentation, then this appears to be a very simple model to do those kind of tasks. Okay, what it appears is that this won't be able to handle those kind of complex tasks. Okay, so because there are very less number of weights to learn, the model complexity is not very high. So this would lead to something known as underfitting if we just remained at this level. Okay, so what we suggest is that rather than using just one filter, we will use multiple filters. Okay, so because we are using multiple filters, different filters can capture different properties of that image, and then in future layers we can merge these properties to obtain the final answer. Okay, so rather than using now just one filter, the earlier filter was blue colored filter. Now we have used one more green color filter, and now we have a 28 cross 28 cross 2. This is our feature now. So we have two features, we have stacked them together, and this is the new feature that we obtained. Similarly, we can have more. So from input, okay, so we used 6 different kernels. Again, these values, what these values these kernels will take, we don't know. We will learn it while training. Okay, and we have stacked it together. So starting from 32 cross 3 image, so we started from this tensor using a 5 cross 5 cross 3, using 6 5 cross 5 cross 3 kernels, we obtain a 28 cross 28 cross 6 tensor. This is one convolution layer. Your one convolution layer would end over here. Okay. So again, you would do everything similar. So you initialize your blue filter by something. You calculate the convolution at this point the same way that we did above. Then you move your this thing based on the stride that you have, padding that you have, whatever you want to do. You will obtain some convolution feature. You will keep that. Again, you will have some green filter that you will initialize. You will again do the same thing to obtain this feature. Similarly, you have obtained 6 features in this layer, and this is one convolution layer. So when we will have an end-to-end training, the values of these kernels will change most probably. Okay. So this is your one convolution layer. Okay. Now what happens is, let's say this was your initial image. You did some convolution. After convolution, you pass everything that you have obtained via some ReLU activation function to incorporate non-linearity. And another thing is, like whenever we talk about colors or image representation, we just take positive values, right? We take values between, let's say, 0 to 256. So negative values don't make a lot of sense. So ReLU is a good choice for activation function. Okay. So from there we did a convolution layer to obtain a 28 cross 28 cross 6 tensor. Then we again applied a 5 cross 5 cross 6 filter. Now here we had applied 5 cross 5 cross 3 filter because we had 3 channels, R, G and B. Now here we have 6 channels, each channel corresponding to a filter in the previous convolution layer. So now we will require a kernel or a filter of size 5 cross 5 cross 6. Earlier we required 5 cross 5 cross 3. Now we will require 5 cross 5 cross 6. Again, this is 28 minus 5 divided by 1 floor plus 1. So this is 24 cross 24 that we'll obtain. Now because we had chosen 10 different kernels, so what it will obtain is this 24 cross 24 cross 10, and you can proceed in the same way. Okay. So we haven't done pooling till now, but till this point is the concept clear? How does this convolution layer works, and how do we stack these convolution layers together? Any doubt in this, you can please ask.
Sir, in case of multiple filter,
Okay.
each filter results with different feature map, isn't it? Or with same, it plays with same feature map.
So each filter will
Results with each feature map, different feature map.
that's what will happen. So what would happen is, for example, over here, we started work with some blue color feature, right? So it will start. So you will have some initial value for this filter, right? You don't know the exact value for this filter. Let's say you initialize with 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So it will obtain a feature map or the convolution feature that I am representing by blue. Okay. For the next filter, let's say green, if you initialize this also to be the same, that you can do, but that can have different kind of challenges. Let's say you initialize it slightly differently. This is 1, 1, 1, 2, 2, 2, 3, 3, 3, right? Now again, it will go over the same image and obtain a different kind of feature map, or you can say convolution feature. We stack these features together to obtain one convolution layer. Okay. So different different filters are obtaining different features for us, but we stack them together in a convolution layer to process it into the next convolution. Was I able to answer your question, or was I not able to understand your question?
Sir, my question is that
Yes.
you have used multiple filter, isn't it, sir? You have used multiple filter.
Here we have 6,
Multiple
here we have
filter,
10.
what you mean is that,
Mm-hmm.
multiple filter, what you mean is that
Mm-hmm.
each filter has different value. Am I right, sir?
Yes, each filter will have different value.
Different values.
Yes.
So, if for example, first filter,
Mm-hmm.
if it is convolved with the input image,
Mm-hmm.
if it is convolved with the input image, you will
Mm-hmm.
get one set of feature.
Yeah. Something like the blue feature that we have over here.
Yes, sir. Yes, sir.
Mm-hmm.
And if it is convolved with second set of filter,
Yeah.
then
Then
you
the
will get second
different
feature,
second feature,
different
the
feature.
green feature. Yeah.
So if it is multiple feature, surely we will get multiple filter. Surely we will get multiple feature. Am I right, sir?
Yes.
Okay, sir. Okay. Thank you.
Yeah, that's what we have obtained here. These different colors represents the different features that we have obtained. Okay. So yeah, before going to pooling, one thing that I want to sort of motivate over here is what happens after this convolution layer is, so whatever last convolution layer you obtain, what you sort of do is you flatten that particular layer, okay, and then you have towards the end a very small, let's say 2-3 layers, normal feed forward neural network or normal neural network that you have. So if this convolution feature that you have obtained towards the end, if you flatten it and it is high dimensional, okay, it is very high dimensional, then the feed forward neural network that will construct on top of it, it will have very large number parameters, okay, and hence it will be difficult to train and all those kind of things. For example, if you look from here to here, when we reached, it was 32 cross 32 cross 3. From there we reached to 28 cross 28 cross 6 after one convolution. Again it is 24 cross 24 cross 10. Okay, so we are increasing the sort of number of neurons. Okay, although the calculation is not increasing, we are increasing the number of neurons. If you flatten this thing and train a neural network on top of it, it would be a very expensive task. Just for the 3 layers you could see this. Okay, now if you do this for something like something that this Microsoft people did, ImageNet, with large number of, I think, 124 or 128 layers, then it becomes very, it would be very compute expensive. Okay, so what we want to do is we want to do some kind of pooling. Okay, so what does pooling does is, so pooling reduces the size of the representation. Because of that, it will speed up your computation and make your features little bit more robust. Okay, so what would happen is, so let's say this is 224 cross 224 cross 64. What does this mean is, so after applying some filter, you get a 224 cross 224 feature, convolution feature. Okay, and you have 64 such uh, filters. This is what does this mean. Now after you have applied the convolution, so you would have applied convolution over here to obtain this. So you use 64 different filters, and after applying one particular filter, the feature that you are getting is of size 224 cross 224. After that, you do the process of pooling. So pooling is done layer wise. Okay, so you will do pooling for one layer, you will do pooling for second layer, and pooling process is sort of not like the pooling in the first layer is not dependent on the second layer, pooling in the third layer is not dependent on the fourth layer, and so on. So from this 224 cross 224 cross 64 tensor, you will just pick 1 to 24 cross 224 matrix. Okay, so you will do this for every 64. So you will obtain 64 such matrices. What you will do is, so this is a single depth slice. Okay, so this is a max pooling with stride 2. So you had a 2 cross 2 sort of window that you placed over here, and you do take the maximum value out of it. So for example, this is your maximum value. From here, this is your maximum value. From here, this is your maximum value. From here, this is your maximum value. Okay. And you replace your existing feature by this pooled feature. So you would obtain from 224, if you do this way, you will obtain 112 cross 112 cross 64, because you are doing it for every 64 channels. Okay. This was with stride 2. Okay. So if you look what it means doing it by stride 1, then it would be clear why it is stride 2. So this is the first thing where you had maximum value obtained. So you obtained 6. Now if you want to do it with stride 1, next sort of window that you should pick is this much only. Okay. So the maximum value is 7 over here, and then you will take this much, then 8. So you will obtain 3 cross 3 then. Okay. So stride 2 is the most common way in which people go for max pooling, so that they get disjoint sort of entries. Okay. So this is the max pool layer, okay, that you use in convolution. Okay, there are other kind of poolings also, that is average pooling. Okay, rather than taking the max value, you can take the average of all the 4 entries that you see in a particular block. Okay, you can also take median, you can take minimum. Like, I'm not sure about where these kind of things would be applicable, but you can do these kind of things. Okay. So this was the max pooling layer. Yeah.
Sir,
Yes.
sir, you've taken 224 cross 224 cross 64.
Yes.
224 is the number of images that is available in the data set, isn't it, sir? Am I right?
No. Right now, what is
Or
happening is,
size of the image?
no. So you had some image. Okay. From there,
Okay.
you have applied a convolution layer and reached till this point. So pooling is done after you have done convolution. Okay. So whatever was the size of your image, from there you obtained some convolved feature of size 224 cross 224 cross, and you use 64 different filters. That's why it is 64.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
So in CNN also, you will only pass one data point at a time. So it won't come in bulk at a time. You will pass one data point only at a time. So it would be image size, and because you have RGB channels, that's why we have 3 channels over there. Those are not 3 different images, but just 3 RGB channels. Okay. So this is a common, or I think this was given by Lee Yukon. Okay, so there are 3 very prominent people in, not 3, but yeah, Geoffrey Hilton and Yoshua Benjo and Lee Yukon. I think they have won the Turing Prize also. So when many people didn't believe in deep neural networks, these people actually did a lot of work in this area. So yeah, so this LeeNet was proposed by one of them initially. This is one of the first CNNs for digit recognition. So so what is happening is, so you have an input image of size 32 cross 32. Right now we don't have any RGB channels over here. There is no RGB channel. This is just a grayscale image. For example, your MNIST data set. Okay. So what is done over here is, okay, so one more thing, this pooling layer in some literature is also referred to as subsampling layer. So if you say somewhere subsampling layer, this is nothing but your pooling layer only. Okay. So on image of size 32 cross 32, this is the convolution layer from here to here. So okay, let's use some other. This is the convolution layer from here to here, and yeah, so there has been 6 different filters, because this is 6 cross 28 cross 28. So they have used 6 filters. Can you guess what is the size of your filter? So if there is no padding over here, right? So this would be 32 minus your filter size, filter width. Stride is again 1 over here. Plus 1 is equal to 28. Okay. So I think the filter size is 5 cross 5 then. Okay. So they have used 5 cross 5 filter, right, to obtain 6 different convolution features. Then they have done here you can apply ReLU also. Before you do subsampling, you can apply ReLU, right? Okay. Like if you apply ReLU before subsampling or after subsampling, it won't make a lot of difference, right? Because if you are taking max subsampling, that shouldn't make a lot of difference. Okay. So then they have done a subsampling. That's why this 28 size is reduced to 14 cross 14. This is the max pooling layer, and the number of channels remain intact. Okay. Then on top of this, they have again applied a 5 cross 5 filter, right? They have obtained 16 such filters. Okay. To do another layer of convolution. Okay. Then they have again done a max pooling layer. Then they have flattened their this whatever they have obtained, and they have trained a small neural network on top of it. Because this is a hand digit recognition, so there are 10 outputs. So there is a classification towards the end. So you will have loss function over here, and this loss functions weight will be propagated. So this loss functions gradient will go back to the first layer to obtain your gradients, and then these filters would be updated. Okay. So now if you look at this particular example, you can see how important choice of activation function and those kind of things become, because you can see there are a lot of layers and lot of computations going on, and if you don't choose your activation functions or those kind of things smartly, then your gradients can become 0, your gradients can explode, and those kind of things. So that's why we devoted a week to this activation functions and all. Okay. So this is how a general convolution neural network looks like. Okay. So there has been many different convolution neural network proposed after that. So there has been ResNet, GoogleNet. There are a number of, you can at least find, I'm not exaggerating, you can find thousands of variants of CNN being proposed. Okay. And some important ones have been covered by professor also. So I'm not covering them again, but I thought one thing that was not very much covered in the course were the data sets that you can use. Let's say from this NPTEL course, you want to do some small project that is related to your image task, right? So what kind of data sets that you should use, what kinds of data sets are available? Okay. So I thought I would include 2 or 3 data sets and tasks that you can do on those kind of data sets. Okay. So the common ones are MNIST and MNIST 100. There are colored MNIST also now available, and those kind of things are available. But MNIST images are not very great for some high level tasks. So these can be used as a verification kind of a thing. But if you want to include it in your CV or those kind of things, you should try some more complex data set. Okay. So this is the ILSVRC challenge for which ImageNet was proposed, and this led to a lot of revolution in using deep neural network for this vision task. Okay, so what kind of data set do we have over here is you have images where it is not necessary that a particular image contains only one image, one category. Okay. For example, when we discussed initial examples where I said that you have some cat images You have some dog images. If you pass the image, you have to predict whether that image is of a dog or a cat. But here the data set is slightly more tricky or challenging. So what you have is you have in a same image you have different kind of uh, like objects present. So there are two-fold tasks that you need to do. First is object detection. So these squares that I have been marked over here are not available to you in the data set. So first task that you would do would be your object detection. And after you have made this kind of detection, then you will have to do the classification. Okay. So this is the ImageNet data set. So for detection task, for this square bounding kind of a task, you have 200 classes and some 457,000 images. Okay. For training data set and some 60,000 images in test and validation data set. 60,000 data set is pretty huge. Right? Okay. And again, for the classification task, you have 1,000 categories where validation and test data set consist of I think this is 1.5 lakhs photographs collected from Flickr and those kind of things. And I'm not very sure, but as far as I can recall, I don't work in this vision background. But as far as I can recall, for the test data set, you have 1,000 images per category. So this should be 1,000 cross 1,000. So I think 10 lakh images for training should be available with you. For validation and test, you have these many photographs. Okay. There is another data set that is Pascal VOC data set. Okay. So here also the task is again detection as well as classification. Here you have lesser number of classes, so you can train better models. This would be more complex than your MNIST data set, but slightly less complex than your ImageNet data set. And images are even, this is a newer data set, so images are even cleaner and of better quality, so you can try this. Okay. So one small thing that I wanted to include is this BGGNet architecture. So this LeeNet architecture was one of the initial architectures, but when you look at any CNN architecture, if you're trying to read some paper or those kind of things, generally they will represent their architecture in this form. So I just wanted to tell you how to read these kind of things. So this is your input image of size, let's say 224 cross 224 cross 220 cross 3. Okay. Then after first convolution, so this black one means that it is convoluting. Okay. So after first convolution, they have obtained 224 cross 224 cross 64. Okay. So they have not reduced the size. Probably they have done some kind of padding over here so that the size does not reduces. And they have used some filters to get the exactly same size, 224 cross 224 cross 64. So this is the number of filters. Okay. You can see this layer is max pooling. So this red one over here would be of size 112 cross 112 cross 64. Okay. Then again there is a convolution plus ReLU, this black boxes. This is 112 cross 112 cross 128. So they have again increased the number of filters. Then again there is max pooling. This would be again 100 and this would be 56 cross 128. Then again there is this convolution, again max pooling, convolution, max pooling, convolution. This is max pooling. Okay. This is 7 cross 512. And then they have flattened this out to a fully connected neural network. And the last layer is your 1,000 categories softmax. So this was done on ImageNet data set. That's why you have 1,000 categories towards the end. Okay. So this is how usually papers would write their architecture, how they would represent their architecture. Okay. So we will do some question on this, but before that, I think I had.
Sir, could you zoom that BGNet again, sir? 1 minute.
Sure. Like this is like the image is nothing special over here. Even if you just type it on the Google, you will straight away get the image. But how to read this, I wanted to tell. Something else also came into my mind that I wanted to tell, but I think skipped my mind. I'll do that. So I just wanted to show you something. I'll search it on the internet first. So this algorithm is known as YOLO. So I discussed the task of image detection. So I want to show you how much progress this deep learning has made in just last 10 odd years. So this YOLO is an architecture. Like in a playing video, what it does is, so when you play a video, it will try to find the bounding box of an object and detect what that object is. Okay, so it's real-time object detection. So there has been, I think, 3, 4 versions of YOLO. So I just wanted to, there is a small video I think available on the internet that I wanted to show you, like how quickly you can detect images. So this, I want to like sort of tell you how far we have reached. Let me search that thing. Because it just came to my mind, so I haven't rewritten that. Just, there is a very neat video. Give me a second. I think, yeah, this video is available here. This should work. I'll share a different tab now. We'll get back to what we were discussing. We'll have some questions also, but you can see this first. No, not this tab. I'll share this tab. Right.
And we're back in third
This is third version of YOLO. I'm not sure if they have released any further.
quarter planning. Adams is quarterbacking this project.
How quickly they are able to watch the video.
I get strung up from her loving. I wish she'd get a seat, but she only cares when she's got the time. And I fret so much about her loving. I wish she'd let me be, but her destiny's got us intertwined. And is it really my fault? I get a shiver when I see her with those other guys, wearing the jacket I bought. I can't help but lose my temper, and I don't know why. I get jealous.
So yeah, so like CNN have reached quite far. So yeah, these kind of things are possible now. People are doing very different kind of things. So if you have looked at the lecture where professor talked about merging two kind of, so you merge texture from something else and picture from something else. Those kind of things are also like common these days. There are many websites that does those kind of things for you, right? So there was a recent trend a few days, I would say few months back, where people used to merge two kind of textures, and if you close your eyes 75%, then you would be able to see that particular texture. Okay, so that was not actually done by a CNN, that was done by diffusion models. But yeah, like people have progressed a lot. So that's the point that I wanted to make. Okay, so there are a couple of questions that are here that I have included. So like we have discussed everything related to the question, so I would like you guys to answer. So can you please try attempting this question? So consider a convolution operation with input image size is 100 cross 100 cross 3. The filter is of size 8 cross 8 cross 3. Stride is 1 and there is a padding of 1. What is the output size? Okay. So formula I can write it again. So you just need to put it in the formula. You can try this thing. This is n input minus 2 times plus 2 times padding minus kernel width divided by stride. You take floor of this plus 1. So can you tell me what would be the size of uh, output? Okay, somebody says 95. Can you?
97.
Okay, somebody says 97, somebody says 95. So let's see. This is what we obtain. So this is 100 plus padding is 2 minus kernel width is 8 divided by 1 plus 1. So this would be 94 plus 1 would be 95. So it would be 95 cross 95 cross 1 because there is only one convolution operation, so cross 1 towards that. So this is also a similar question, but here you will see why do we use the floor function. I think this is the only question where you will be able to see why do we use floor function. So please try calculating this example, like whoever has not done the last part also, please try doing this. So the only unique thing in this is that you have a higher value for stride. Stride is 4 over here. Padding is again 2. So please try this question. Okay, somebody says A. Others can also try, please. Okay, so 2 people have tried responding, so I'll try to solve. So again, the formula remains same. So it is n input. Input is 256. Padding is of size 2. So 2 cross 2 is 4 minus kernel width is 11 divided by 4. And we take floor of this plus 1, right? So this is 260 minus 11. This is 249 by 4, right? Floor plus 1. So this is 62 point something, right? 62 point something. If you take its floor, then it is 62 plus 1. So 63 is the correct answer. Okay. So this is also a similar question. So we can skip sort of this question. This is also pretty similar. So you have 9 cross 9 image and filter is of size 4 cross 4. What is the resultant dimension? So 9 minus 5, 9 minus 4 plus 1 should be 6 cross 6. Nothing much to do over here. Okay. So you can read this question. This is also similar. So you can attempt one of them. Okay, so there is a this format is such that d at the rate d represents over here the number of channels, okay, or the depth of the layer, okay. H is the height, W is the width, okay. S is also stride is all for operation, all operation. What is the dimension of individual filter in the initial layer? Okay, so this is 8 filters of size 128 cross 128. So dimension of individual filter is 128 cross 128. No, sorry, that is the feature. We have to find the dimension of initial filter. Is the filter initial. Okay, so the first time where the convolution operation is taking place is this. Okay, here we have max pool, here we have convolution happening. So let's try to find the size of the filter over here. Okay, what is the size of filter? So here we had 8 depth of size 64 cross 64. From 64 cross 64 we have gone to 48 cross 48. So output is 48, which is your input is 64 minus x. There is no padding, right? Plus 1. So we can have 47. So 64 minus 47 would be the size of filter over here from going from here to here, right? And this is the first place where convolution is happening. So this should be the correct option. I think either they meant something else in the question, they should have included something here. But if we treat this thing to be the question, then this would be the answer. And what would be the depth? Depth would be 8. So this is 3 and 4. 3. So 17 cross 17 cross 8 should be the size of individual filter in this initial layer. We treat this to be the initial layer. Okay. How many filters are there in the initial layer? If now we think this is the initial layer, then there are 8 filters over here. Right. Here also we have 8 filters. Here we have 24. Here we have 24. Okay. So this is what I had prepared for today. I wanted to sort of go slow on the idea of CNN. How does that work? So I know that I have skipped a lot of things that was there in the lecture, probably different kinds of architecture and those kind of things. But I think the second part, especially where you have to optimize with respect to image, professor has explained it very well. So I didn't found much that I can do and fit it in this time. So this is sort